What do we have? Proofs of identities involving mod and arg. I have to prove mod z1, z2 equals mod z1 times mod z2. Actually, this one might even be easier in polar form. But let me show you can do the modulus in Cartesian form. Let z1 equal a plus bi, z2 equals c plus di, a, b, c, and d are real numbers. Why do I think it's important to say a, b, c, and d are real numbers? I'll let you catch up. Wasn't it be a B, not a line with a short line next to it? What would happen if one of these was not real? What's the alternative? If it's not real, it could be complex. What happens if A is complex? Well, I no longer know what's the real part and what's the imaginary part, and that's going to matter. If D is complex, well, suddenly I've got something times I, I'm going to get a real part out of this complex part. So I need to be sure I know exactly what I'm talking about. Okay, left-hand side is mod z1, z2. That is the length of a plus bi, c plus di. Expand the brackets. No. And put all your real terms together and all your complex terms together. Collect your real terms and your imaginary terms. Why? Because then I can find modulus. How do I find the modulus of any complex number? And if you've written 80 plus BC, that's just as valid. Won't change anything. Keep expanding, keep simplifying. Real part squared plus imaginary part squared. Yeah, it's going to be a mess of letters. And then you're going to go back and do the same thing on the right-hand side and show you get the same mess of letters. What have I got? A squared C squared minus 2ABCD plus B squared D squared plus, it's long, And two of those terms cancel out. Beginning to think I should have done the polar form. Might have been easier. How do I simplify that? No, what am I doing? A squared. A squared C squared plus A squared D squared plus B squared C squared plus B squared D squared. Oh, look at that. For two or three of you on the exam you just did, it looked like if this had been an exam question, you would have got to about here and stopped and gone, this is getting me nowhere, I give up. I want to encourage you. Most of you are good at algebra. Keep going, keep going, keep going, keep working it, you'll get to a solution. Arg is harder. In fact, arg is very difficult to prove using Cartesian form. So let's try polar form. I need to prove arg z1, z2 equals arg z1 plus arg z2. Now, this is kind of what we told you about how complex multiplication works. But it is possible to prove it using just cos and sine. Instead of Cartesian, let's go. Z1 equal R1 cis theta 1 and Z2 is R2 cis theta 2. Now I said over here it was important to mention their real numbers. Here, because of the convention, we know this is an angle and this is a non-negative real number. It has to be. If you wanted to, you could write that, but no one ever bothers. So what do I know? let's go. Arg of Z1, whoops, Z2 is the arg of R1 cis theta 1, R2 cis theta 2. Well, for that I can ignore the, well actually let me go like this. No, maybe I should say that. I'm going to be able to ignore the length. They've got nothing to do with the argument. It's supposed to be an equal sign. I think I'm going to get tired of writing cis all the time. So let me just look at what happens in the middle. Arg cis theta 1, cis theta 2. No, sorry, I meant to do it without the arg, didn't I? Oh. Cis theta 1, cis theta 2 is cos theta 1 plus I sine theta 1 times cos theta 2 plus I sine theta 2. Bless you. Expand the brackets.
Do we have to do this though? Because like, don't we know that when you multiply,
If the question says to prove it,
you have to do all of it?
then show me that you really know why this works. Yes.
Okay.
Yes. We've invented cis as a notation. Show that this really works. Year 11's about to get another introduction to the trig identities on the formula sheet.
Yeah.
And Eddie's going to see if he remembers which one to use when we get there. Expand the brackets. Cos theta 1 sine theta 2 I. No, what am I doing? What am I doing? Cos theta 2 plus I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2 plus I squared sine theta 1 sine theta 2. Be careful, some of those 1s and 2s are subscripts. One of those 2s is a superscript. I squared is -1. Collect the real terms and the imaginary terms. Be careful with the 1s and 2s. You're probably better off doing it from your paper in front of you and then checking that you've got the same thing as I have. And Eddie is doing the right thing. Quickly whip out your formula sheet and find the correct identity on page 4 to apply for each one. And it better be cos of the sum and sine of the sum, right?
Oh, I mean, you can do either.
No, think about what we want to end up with, Eddie.
Yeah, but you just keep rearranging.
Think about what we want to end up with, Eddie.
Cos plus I.
Look at what we're looking for. Pardon me. So So whip out your formula sheet and look on page 4. Okay, the real part is cos, minus sine, sine. And if you look up here, cos, minus sine, sine is equal to cos of the sum of the angles. So I can replace the real part with cos theta 1 plus theta 2. That's nice, that's what I want. The imaginary part goes cos sine plus sine cos. Cos sine plus sine cos. Because it doesn't matter which order you put the A and the B in this one. Cos sine plus sine cos is sine of the sum. Plus I sine theta 1 plus theta 2. Oh, that's nice. Because that is cis theta 1 plus theta 2. And now I can finish my proof. So that means the left-hand side equals arg of cis theta 1 plus theta 2, which is theta 1 plus theta 2, and my right-hand side is arg of R1 cis theta 1 plus arg of R2. Oh, I should leave myself more room. I really needed to leave myself more room, didn't I? Plus arg of R2 cis theta 2. You should be able to see where I'm going now. That's theta 1 plus theta 2, which we now know is the same as the left-hand side. Now, you have proven this, the modulus bit, and you have proven this, the argument bit. You don't have to prove them again when you're proving some of these other ones. You can say, oh, from identity 1, from identity 2, things you've already proven, you can say that's okay, I can do that. Z times its conjugate is equal to its length squared. Okay, let Z equal A plus BI. A and B are real. Okay, the left-hand side is Z times Z bar, which is A plus BI times A minus BI. So here again, if B wasn't real, I couldn't say this was necessarily the conjugate, because there'd be some other complex bits in other places. Expand the brackets. Go. Collect real parts and imaginary parts. Minus ABI plus ABI minus B squared I squared. What's the length of z? What's the mod of z?